The first Hwknn-aware classifier we are going to study is essentially a weighting scheme for nearest neighbor classification. Therefore, we will now review weighted nearest neighbor. In case of the weighted nearest neighbor classifier, the training instances are associated with so-called weights. These weights are real numbers. In this example, we are going to classify instance 11, this triangle. So this is the instance for which we want to determine whether this instance belongs to the class of rectangles or to the class of triangles. And we calculated 3 of its nearest neighbors, and in this example you can see the weights of these 3 nearest neighbors. The weights of these nearest neighbors may be given by the user, so they may be contained in the dataset, or the classification algorithm may somehow calculate these weights. At the moment, we don't care where the weights originate from. We are only interested in how to classify this new instance once the weights of the nearest neighbors are given. And what happens is that the nearest neighbors vote according to their weights. And therefore, the sum of the weights for the class of circles in this example is 2.5, because only one of the nearest neighbors belongs to the class of circles, and this particular nearest neighbor, in particular instance 6, has the weight of 2.5. Now, the sum of the weights for the class of rectangles is 1.2 plus 0.85, that is 1.87 in total. This is the sum of the votes for the class of rectangles. And in this example, the sum of the votes for the class of circles is higher than the sum of the votes for the class of rectangles, so this instance will be classified as a circle. It is important to note that generally what we consider is the sum of the votes. So the reason why this triangle is classified as a circle is essentially not the fact that the nearest neighbor with the highest weight belongs to the class of circles, but the fact that the sum of the weights for the class of circles is higher than the sum of the weights for the class of rectangles. In order to illustrate it, let us consider a second example. In this second example, we want to classify the triangle again, and here the 3 nearest neighbors are instance number 6, instance number 7, and instance number 8. And here the sum of the votes for the class of rectangles is 1.76 plus 0.92, which gives in total 2.68. So the sum of the votes for the class of rectangles is essentially higher than the sum of the votes for the class of circles, and therefore in this case this triangle will be classified as a rectangle. So in this case, this weighted nearest neighbor classifier gives the same result as a simple nearest neighbor classifier. As I mentioned, the first Hwknn-aware classifier is essentially a weighting scheme for this previously shown weighted nearest neighbor classifier. In particular, the weights are calculated based on the fact how frequently an instance appears as bad nearest neighbors of other instances. Of course, this can only be calculated for the instances of the labeled training data. Because for new instances, for those instances about which we don't know whether they belong to the first or the second class, or generally to which class they belong, for these new instances, of course, we cannot calculate if they appear as good or bad nearest neighbors of other instances. So we can only calculate for the labeled training instances how frequently these labeled training instances appear as bad nearest neighbors of other training instances. And what we want to do is to reduce the influence of those training instances which frequently appear as bad nearest neighbors of other instances. Therefore, those instances that appear frequently as bad nearest neighbors of other instances will be associated with a low weight, whereas those instances which never or just rarely appear as bad nearest neighbors, they will have a high weight. In order to implement this weighting scheme, for each instance we calculate b and kx, that is, how many times this instance appears as bad nearest neighbor of other instances. Subsequently, we calculate the average and standard deviation of b and kx for all the instances, and then we can calculate the so-called normalized bad Hwknn score of an instance, as you can see in this slide. Then, this normalized bad Hwknn score is used to calculate the weights of the instances. In particular, we raise e to the negative power of this normalized bad Hwknn score. The next slide illustrates this classifier using a numeric example. In the top of the slide, you can see for each training instance how many times this instance appears as one of the bad k nearest neighbors of other instances. For simplicity, we use k equals 1 in order to calculate how many times an instance appears as the bad nearest neighbor of other instances. However, in order to be able to illustrate weighted classification, we will use k prime equals 2 nearest neighbors while we are classifying the triangle. The two nearest neighbors of the triangle are instance number 6 and instance number 9. And in order to calculate the weights of these nearest neighbors, what we need is the normalized bad Hwknn score of instance number 6 and instance number 9. As we have already calculated b and kx for each training instance, we know that the mean of b and kx is 0.3, whereas the standard deviation of b and kx is 0.675. So, the normalized bad Hwknn score for instance number 6 is simply the b and kx value of instance number 6 minus the mean of b and kx divided by the standard deviation of b and kx. In particular, in this case, the normalized bad Hwknn score of instance number 6 is 2 minus 0.3 divided by 0.675. So, e is raised to the power of this negative normalized bad Hwknn score, and then we get the weight of instance number 6, which is, in this example, 0.0806. Similarly, we can calculate the weight of instance number 9, and this will be, in the end, 0.3545, and the reason why instance number 9 has a higher weight is that instance number 9 only appears once as bad nearest neighbor of another training instance. So, we trust instance number 9 somewhat more than instance number 6 because instance number 6 appears twice as bad nearest neighbor of other instances. Taking these weights into account, the new instance, this triangle, will be classified as a rectangle.